So I'd like to take some time to go over the conditions or the requirements necessary for all of the procedures that we've done this spring and show you hopefully how all of these things work together. So I think that you can see after we go through this that it's all very, very similar, just with different applications each time. So back at the beginning of the semester, we talked about the z procedures for means, looking at x bars and comparing it to a mu. And we started out with a one sample problem. And we had three conditions that had to be met. First of all, we needed a random sample. Second of all, we needed to know sigma. And third of all, we needed to have a normal population. And if those things were met, then we said, well, we can use, therefore, I will use the one sample z procedures for means. Now, these are really conditions that have to be met, and so we check those conditions, and if those conditions aren't met, we might have to assume that those conditions are met. For example, if the problem didn't tell us that we had a random sample, we can't check that condition because that information is not known, but we could say something like, boy, I sure hope that the people who took these samples did it in a way that got a simple random sample or something like that. And if we met those conditions, we could use either of these two formulas. This one, if we had a confidence interval, and if we had a hypothesis test, then we did something like this. And I want to kind of talk about that for just a second. What we've got in the hypothesis test is the test statistic equals the estimate minus the parameter over the standard deviation of the estimate. And so the estimate was x bar and the parameter was mu, and the standard deviation is that sigma over the square root of n. If it's a confidence interval, then it's the estimate plus or minus some critical value times the standard deviation of the estimate. And those formulas that I just wrote in black will continue throughout the whole semester with slightly different applications in each one. And then after we did this with Z problems, we switched gears and we said, you know, what if I have an SRS and I don't know sigma? Well, that's when we went to the t distribution, and we also added a little wrinkle onto this population as normal bit. We either wanted the population to be normal, or we had a way of relaxing that a bit, and we said we could have, if we had a large population, sorry, a large sample, then we are good due to the central limit theorem, telling me I'll end up with something that's approximately normal. Or I have a medium sample, and I'm good there, provided that there's no good, provided no outliers or extreme skewness. Or I have a small sample, and I'm good if I have approximate symmetry. And these Small, medium, and large distinctions. We said basically small was something less than 15, and a medium was somewhere maybe between 15 and 30, and a large was, say, bigger than 30. Some books use 40, and that's okay as well. And if I'm going to have to do one of these three bullet points here, then I need to actually graph the data and show them what I've got. So I'm actually going to sketch it out on here. I don't necessarily have to put all the niceties, but I've got to sketch it and go, whew, good thing this medium sample has no outliers or real bad skewness. Check it out. It's right here. And if all that was met, then I would say, therefore, I will use the one sample T procedures for means. And we added this little bit on here with n minus 1 degrees of freedom, whatever that happens to be. And the formulas follow that same pattern we did before. For a confidence interval, it's the estimate plus or minus a critical value, which is now t, and the standard deviation of the estimate is now s over the square root of n. Or for a test statistic, the test statistic was t. The estimate is x bar minus the parameter mu over, again, s divided by the square root of n. And so those were our one sample procedures. So from here, we said, you know, what if I had two samples? So I'm going to go to a new slide here. What do I do with two samples? Well, basically with a two sample problem, I need to check the conditions that we listed up here, whether it's going to be a Z or a T, with the added condition that my samples are going to be independent of one another. So if it was Z, then I would need both samples are independent. Check previous conditions for both groups. And if that worked, then I could say, therefore, I will use the two sample Z procedures for means. And the formulas, and again, what I'd encourage you to do as I go through this is to pause the video and anticipate what I'm about to write next so that your brain is engaged in how all this looks. So it's not just a giant amount of memorization, but rather a pattern that's just getting applied to different arenas. So I've now got for my formulas x bar 1 minus x bar 2 plus or minus a critical value, and then the standard deviation is sigma 1 squared over n1 plus sigma 2 squared over n2. Now, I don't know if we actually did this part of the formula in class this year, because what we ended up doing was going straight to the T procedures. But the pattern still holds, which is why I'm writing this down. And so this is going to be Z equals x bar 1 minus x bar 2 minus mu 1 minus mu 2 all over the big square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And we said this little part here is typically going to go away and go to 0 when I have an HO that says mu1 equals mu2. Now, with the T procedures, this is going to look very, very comparable. This stuff here is going to just slide right on over. This sentence is going to say, therefore, I will use the two sample T procedures for means. And then we got to talk about degrees of freedom again. Now, we talked about two different ways of doing degrees of freedom for these problems with either the calculator degrees of freedom, whatever it told me with that long formula that we don't have to use, or the conservative degrees of freedom, which is the smaller of n1 minus 1 and n2 minus 1. That's the more conservative degrees of freedom. Um, and then my formulas look very, very similar to what I did on the left in green, except I'm going to use T instead of Z, and I'm going to use S instead of sigma. So it looks like this. X bar 1 minus X bar 2 plus or minus T star times the square root of S1 squared over N1 plus S2 squared over N2, or T equals X bar 1 minus, minus X bar 2 minus mu 1 minus mu 2. And again, that part is probably going to go away, at least in the intro stat course that we were covering. S1 squared over N1 plus S2 squared over N2 and the square root of that. And there's my formula for the test. So there was one other kind of problem that involved means, and that was when we had two samples, but the samples weren't independent. They were actually matched together. So maybe, for example, the first list is strength with my left hand, and the other list is strength with my right hand. But the numbers match up because the first number in each column is me, and the second number in each column is you, and the third number in each column is our friend Todd, and the next number in each column is our friend Mandy, and so on and so forth. And so the numbers are not independent. They're actually matched. And this is called a matched pair problem. And basically what I want to do in a matched pairs problem is I'll consider this when my samples are matched, and therefore they're not independent from each other. And what I'm going to do is subtract those two numbers and find the difference, usually like L1 minus L2. And then I'll use the previous conditions from what we talked about earlier. In other words, I'm going to treat this as a one sample problem on the differences. Maybe I examined 10 students and I asked them their math score on the last test and their English grade on the last test, and I put these in L1 and L2. Well, in L3, I'll subtract those numbers to get the difference in their scores, and I'll perform a procedure on that L3, checking the conditions on that. And typically there, my HO is going to be that mu equals 0, or in other words, there is no difference between the two groups. So those are the procedures that we did on means, and now I want to move into proportions. So as I did before, we'll start out with a one sample proportion problem. And I guess now is a good time to talk about the distinction between a proportion problem and a means problem. Proportion problems deal with categorical data, where if you ask the individual a question, they would give you a yes, no. So I would say, hey, sports fan, do you enjoy watching soccer? And the proportion of yeses would be on top. And that's different than saying, hey, sports fan, how much money did you spend at your last sports event? That would be a means problem. So, one proportion problem, similar things to what we said before. I need to have the sample be a random one. I need to have a normal distribution, which gives me at least 10 successes and failures. This is actually called our large counts condition. And I need to have a 10% rule being met. The 10% rule is important when I am sampling without replacement. And if those things are met, then I would say, therefore, I will use the one sample Z procedures for proportions. And my formulas are going to look just like they did before. It's going to be the estimate, which is now p hat, plus or minus a critical value, z star, times the square root of p hat 1 minus p hat over n. That's the standard deviation of the estimate. For the hypothesis test, I've got my test statistic equals the estimate minus the parameter over the square root of p times 1 minus p over n. Now notice the difference here. What I'd prefer to use down here is p and 1 minus p. But on a confidence interval, I don't know p and 1 minus p. Here I've got it because I've started with some assumption like, say, p is 0.7, and I can stick a 0.7 down there. But I don't know what p is up here, so I have to use my next best thing, my guess, my p hat. And so that's what the difference is on these two. And of course, if you were asked that, they would definitely be looking to see if you could remember that distinction. Then we also have two sample problems. It should be and just like before, two sample is very, very similar to one sample, except now we want to look at this for both groups. So I need the two groups to be independent. And then check those conditions for each group or each sample. Those conditions over there. And then I could say, therefore, I will use the two sample Z procedures for proportions. Remember, there's no degrees of freedom here because these are Z problems, not T problems, so I don't have to worry about degrees of freedom. And my formula now is going to look like this, just like before. It's the estimate. I've got this now, plus or minus a critical value, times the square root of p hat 1, 1 minus p hat 1, all over n1, plus p hat 2, 1 minus p hat 2, all over n2. Write that a few times because it looks a little tricky and it's easy to get confused. Now on the hypothesis test, we've got a little wrinkle thrown in here, and it's going to look like this. Z equals p hat 1 minus p hat 2 minus p1 minus p2. And again, that's the part that, at least in intro to stat, that last parentheses goes away when I assume the two proportions are equal to each other. Now on the bottom, under this square root, I end up with what we call the pooled p hat right here. No subscript there. There is a subscript on the n1 and n2. And this is where p hat is the pooled proportion. And so the way you find p hat is something like this.
P hat equals the number of successes in each group added up over the number of attempts in each group added up. I realize that's not normally how you add fractions, but really I'm not adding fractions, I'm combining proportions. And so that's what goes on here. This happens automatically. This pooling, when you use your calculator, occurs automatically. And I failed to mention this before when we were looking at a T problem. On your calculator, it's going to ask you over here if you want to pool and you do not want to pool. So say no on these problems when it asks you. That's another concept that we don't cover. But here, it happens automatically because you're assuming, so I'll write that on here, I guess, since your null hypothesis is that the two groups are equal to each other. If that was not your null hypothesis, this pooling would not naturally occur. Now beyond this, we move into a chi-squared test. And a chi-squared procedure is done when we have multiple groups of proportions, two or more. If we had two proportions, we would do what we just did. But we could do chi-squared, and certainly if we had more than two, we would do chi-squared. Now, one difference with chi-squared as opposed to proportion problems is the first condition. I deal with counts. And by counts, I mean the actual number of successes. I don't change them into decimals or percentages. I work with the actual counts that are on there. And then we need all the expected values to be greater than 5. Some textbooks will teach that most of the expected values need to be bigger than 5, and so if you had one small group or less than 20% of the groups to be less than 5, you'd be okay. But we'll leave it at this for now. And if this is the case, then you would say, therefore, I will use the chi-squared procedures. And there's actually 3 different chi-squared procedures that we talked about. One of them was called goodness of fit. And this is when I had a list, and the degrees of freedom were categories -1. We also talked about a test for independence. Whereas when I'm going to have a table or a matrix, and the degrees of freedom equals row -1 times column -1. Or I've got a chi-squared test for homogeneity. And again, that's when I have a table and the degrees of freedom, just like a test for independence, are row -1 times column -1. And if you kind of want to know the distinction, it sort of looks like this. This is when I have a one sample, one variable problem. So that's why it's in a list. With a test for independence, I've got one sample. I only ask one group of people, but I ask them 2 different questions. And so I end up with a table where the 2 variables that I asked are on one's on the side, one's on the top. And then a chi-squared test for homogeneity is going to be 2 samples. And I've got 2 variables there. And I guess I could say 2 or more samples if you ended up in a different kind of matrix. So I have, say, a group of boys that I ask some questions, and I ask a group of girls, and so my variables are were you a girl or a boy, and then how do you end up answering this question, which is different than saying, hey, large group of people, tell me your gender and the answer to this question. So in a test for homogeneity, I've got multiple groups, and I want to know if they're broken down the same way. In a test for independence, I've got one group, and I want to know if these two variables within that group are related. But the mathematics and the mechanics of working these tests are the same. And the formulas that we had in here was that a chi-squared test statistic was going to be the sum of observed minus expected squared over expected. So I find all those numbers and add them up. Put this up here. And the expected values were found a couple of different ways with a table. The expected values were the row total times the column total over the table total. And your calculator will do those values for you automatically when you use the function. And finally, the last procedure for the year is inference on slope. So now we're going to do it like a linear regression problem. And we've got a couple of conditions that we need to have with this. Our book uses this acronym. I think I was doing these in red. For the conditions here. And what I need is a true linear relationship. If I'm going to talk about the slope, I need to have a linear relationship. I need to have independent observations. If I was sampling without replacement, this would be the 10% rule. I need normally distributed residuals. I need equal standard deviation of the residuals from the line, and I need a random sample. And so to check these, I'm gonna assume or check that condition for randomness as well as independence in the actual problem to see if there is a linear relationship. This is where I look at a residual plot and say, is there a pattern here? For equally distributed residuals, again, I'm looking at the residual plot. Sorry, equal standard deviation of the residuals, I'm looking at the residual plot and asking about the spread. Does the fanning increase or decrease? For normally distributed residuals, I'm going to make a histogram of the residuals and see if it kind of looks like that. And if that's the case, then I would say, therefore, I will use inference on slope with the T procedures and n minus 2 degrees of freedom. And n is the number of data points that I have. So n minus 2 there for the degrees of freedom on these problems. And the formula is going to be T equals the estimate minus the parameter divided by the standard error of the estimate. And we had a bunch of formulas that went through this chapter, but that's the formula for the test statistic. And for a confidence interval, it's the estimate plus or minus a critical value times the standard error of the estimate. So those are the procedures and the formulas and kind of how they all fit together. And hopefully you've seen some commonalities with all of this stuff throughout the semester.